You are welcome to this lecture. This is in continuation to our earlier discussion, where we are trying to analyze the plate fin type heat exchanger of multiple, where multiple streams are handled, and we talked about the fin temperature profile connecting between the two surfaces or connecting between the plates at temperature T A and T B, and we said that the temperature profile between the plates were known to us, and we have derived some kind of, we have obtained some kind of temperature difference or temperature profile theta x equals to theta a multiplied by omega into to the power x. It was of this nature, 1 minus omega into e to the power mx plus omega into e to the power minus mx, where omega is having a relation between r and sine hyperbolic ml. And then we also tried to find out the amount of heat getting transferred. So, this is say T A and T B. We have the temperature profile for this fin connecting between T A and T B. If the fluid flowing on top of this fin is of temperature T 0, then we have been able to find out the total amount of heat getting transferred as a function like this 2 h multiplied by theta x into dx, and this integration was done over the length 0 to L. This is 0 and this is the length of the fin L. So, from here we got the total amount of heat transfer when the adjacent fluid streams are T A and T B. Now, this is exactly what we are looking for in case of a multiple fluid stream. If you look at that particular geometry. So, if it is a 5 fluid stream heat exchanger, say we have T W 0, then we have T W 1, then we have T W 2. These are the wall temperatures, separating wall temperatures. Then we have T W 4 and T W 5, and we have for 5 fluid stream depending on their configuration. So, maybe they are in counter current to each other, or it may be a parallel counter combination. So, that will be automatically taken into account if we are able to write down the fin equations and the plate equations separately. So, if we now try to find out the heat transfer taking place through one single fin, that is what exactly we have told, that this is the Q T amount of heat getting transferred, and that was given as as we have estimated it earlier, that it would come as H into L into theta A plus theta B and tan hyperbolic eta of fin half. So, as if half of the fin is attached to this place this plate, and half of the fin is attached to this plate, and as if there is a kind of adiabatic temperature profile condition prevailing at the fin middle. So, this is like this is T A T W, T A and T B, and these are actually nothing but T W 0 and T W 1. This is in this nomenclature they are T W, in this nomenclature we have talked about T A T B. Now, if that is connected by two fins, and we can show that when this T A equals to T B, we will have a minima at the or a maxima at the middle of this fin, thereby depending on the temperature of the fluid flowing on top of it, we will find that the heat either is flowing from this wall to the fluid or fluid to the wall, but there is a minima at the middle of this fin. So, that means some kind of adiabatic condition has been set at the middle of it. So, half of the fin is as if attached to this plate and half of the fin is attached as if to this plate, but it may not be the situation for every cases where T A and T B are not the same. So, depending on the T A T B, we may find various kind of configurations where we will find that the extremum or this minima or the maxima is lying within the fin, outside the fin, and of course, it may be there is no minima at all. So, there may be situation. So, in those cases, how are you going to take account of those situations that we want to discuss in this class, and we will start with the basically the fin equation again. So, now if we look at, we will find that this the fin equation we have already talked about. Now, if we want to look at the maxima or the minima in that fin equation, we have to take a derivative of that equation, fin equation, and equate it to 0, and then we can determine what is the position of the maxima or the minima. So, we have theta x known to us. What we do is that we differentiate it with respect to x, and then we equate it to 0. So, this will lead to the situation that theta a and 1 minus omega and e to the power m x, there would be another m here, then we will have minus omega into m into e to the power minus m x, and that has to be equated to 0. So, this will lead to, if you do a little algebra, you will find that e to the power 2 m x is equals to omega by 1 minus omega, and that will be with little bit of algebra you will find that this is coming nothing but e to the power m l minus r by r minus e to the power minus m l. So, this will tell the exact location of the extremum that is occurring in terms of this fin connected between the two plates, as we have told that this has been taken from the paper by, it is available with Prasad P-R-A-S-A-D, and it has been taken from International Journal of Heat and Mass Transfer, volume 39, issue 2 of 1996, or otherwise you can also refer to the book of Shah and Shekulik. There also this analysis is available. So, if we have this fin connecting between these two wall which are at say T A T B, and they are connected by a fin of length L, and we are trying to find out where is the extremum that is located depending on the as you can understand that this r and e to the power m l and that ratio will determine where exactly this x is getting located. Particularly if we say that r is equals to 1, that is equals to e to the theta b by theta a, that is what is r, and that means theta b is equals to theta a, you will find that this x is coming exactly at L by 2. So, that means we find that when this temperature or these two temperatures are equal, we have an extremum located at the middle, and that means we have L by 2 fin attached to this plate and L by 2 fin attached to this plate. So, if that is so, if there is a kind of adiabatic condition at the middle of that fin or anywhere at the fin, we can assume that there exists a kind of adiabatic condition or at the fin tip, and we can easily use that eta f equals to tan hyperbolic ml by ml. That was the fin efficiency, provided we know the exact location of that extremum. But as we have said that this corresponds to a particular situation where this half of this fin is attached to this, or half fin idealization as it is called. Then it is possible only when this TA TB are equal, but in reality you may find that there are several situations where TA not equals to TB, and in those cases we have to go for a different how do we estimate? One way of doing the estimating the thing is that we try to find out exactly what is the up to which that extremum is located, where it is exactly located. And if we look at to this diagram, we may be it may be a situation where you will find that this is like TA, this is TA, and this end is at TB. This temperature is TB, and the fluid temperature flowing on top of that fin is at T0, and its minima is somewhere at this point x, where the length is the total length is L. So, now in this case we have the extremum located at this point, and we may try to find out the position x, and that will be given by e to the power 2 mx is equals to e to the power ml minus r by r minus e to the power minus ml. So, from there from depending on the temperature and this temperature ratio theta a by theta b and the value of m and value of L, we would be able to find out the position x where the extremum is located. So, we have x and then L minus x, these are the two lengths over which we have to calculate the heat transfer. So, how do you do that? So, we will be able to find out two integrals where we should be able to calculate it over this two lengths. One is say if we tell it as QA, that is the heat transfer taking place from this fin, and this is from this side, this plate to this fluid, and from this plate to this fluid is this is QB if we try to find out, and this is nothing but we have already tried to find out that one earlier, and this would become twice x into h into theta a and then eta a. As because we have assumed that, or not assumed, means we have told that there is an extrema at this point. So, that means there is an adiabatic plane at this point. So, we know that we have an adiabatic plane or at this point. So, fin tip, which is the fin tip, where is the fin tip? The at distance location x, and what is the temperature difference here up to this point? Theta a. Then what is the heat transfer coefficient is h, and this eta a is taking care of that fin connected between this wall and this length. This is the adiabatic condition prevailing at this location. So, this is at TA, and this fin temperature profile we have already known to us, and what is the length? This entire fin is not at TA. So, what is taking care of that one? That we have, you see, we have not written it as theta x or variable length. So, here we have put it as theta a, as if this entire fin is at the fin base temperature TA. So, we are multiplying it with the fin effectiveness or fin fin efficiency rather, eta A, and multiplied by the heat transfer coefficient, and this is the length of the fin. So, by that way we would be able to calculate Q A. Similarly, we would be able to calculate Q B, and you will find Q B would be twice L minus x into h into theta b, and then you have eta b. So, this is what is the amount of heat getting transferred from the wall B to the fluid. So, this is 2 L minus x into h into theta b and eta b. Here we are finding that this remaining length of the fin L minus x is having, as if there is heat transfer coefficient h between the fin and the fluid, and the fin is as if the entire fin is at a fin base temperature of theta b, which is not actually the case, but this fin efficiency is taking care of that one, so that this entire fin base is assumed to be at theta b. So, this is Q A and Q B. Now, if you put the values of Q A and Q B, you will find that their Q A is coming as root over 2 h k t and theta A, and then we have cos hyperbolic m L minus r divided by sin hyperbolic m L. Similarly, Q B would be it would be root over 2 h by k t, 2 h k t, and then you have theta A, then multiplied by r into cos hyperbolic m L minus 1 divided by sin hyperbolic 1 sin hyperbolic m L. So, this is what is Q B and this is Q A. So, that gives you the temperature, the heat getting transferred from this plate to the fluid and this plate to the fluid. This is Q B and this is Q A. So, once we know this Q A and Q B, we would be able to find out many things. Now, as we have told that it may not be always the situation that this fluid temperature, you cannot expect that it will be in this configuration. There may be other situations like this fluid temperature may be just the wall temperatures, this is here, and this may be at this point. So, that means this T0, the fluid temperature may be hotter than the wall temperatures. So, in that case what will happen? The heat will be getting transferred from the wall, from the fluid to the wall. So, only thing that we need not worry about. So, what we have to do is that we have to just this automatically that will be taken into account once we are able to once we are able to once we frame the equations, it will be automatically taken into account. This Q B or Q A, it will automatically take into account of this temperature. But the situation will really be different. All these things depend on that equation where we have said that e to the power m x is equals to e to the power m L minus r divided by r minus e to the power m L, and this r will determine the position of the x, and that r is basically nothing but the theta b by theta a. So, if r is such that theta a or theta b is such that this location of this x is going the physical boundary of this fin, it may lead to a situation that x is no longer, the extremum is no longer existing within this physical boundary of the fin. So, which means that at exactly r equals to, if we put 1 by cos hyperbolic ml exactly at 1 by cos hyperbolic ml, when this is the value of r, then we will find that this extremum is exactly at this location, and when we have values are when the value is r less than 1 by cos hyperbolic ml, then it will indicate I mean, let us look into that situation one by one. So, here we have a situation when we have say exactly r is equals to 1 by cos hyperbolic ml. So, at that point the extremum is located at this point, and we will find that exactly at that point the situation will be such that it is continuously from this end to this end. And for values r less than 1 by cos hyperbolic ml, you will find that this is going beyond the physical boundary of the fin. So, here in this case we will have the fin extremum located at this point. So, is it making any kind of changes in the fin equations, or in what does it physically mean? You will find that it is meaning that how is the fluid flow configuration here in this case? The fluid is at a temperature T0, this wall is at a temperature Ta. Now, the heat is getting transferred from wall to this fluid, and also Tb is higher than the fluid temperature. So, the heat is getting transferred from this wall to the fluid. So, both the wall are giving fluid to this temperature in this configuration. Now, if we look into that QA and QB expression, okay, and if we look into its configuration, I mean its expression, and there if we look into a situation where r is less than cos hyperbolic ml, under this condition you will find that in this configuration what you will find is that in this situation you will find that this QA it is positive, or I mean heat is coming from this wall to the fluid, but this will have a change in the values. So, here instead of heat going from the wall to the fin, you will find that the fin is giving heat, the fluid is giving heat to the wall. So, this is in contrast to the earlier I mean situation, and it will lead to a kind of direct heat transfer from this wall to this wall and bypassing the fluid stream, and we often call it as the transverse heat conduction, or we have to I mean this has to be either taken care of separately, or we have to define a fin efficiency to take care of this bypass heat transfer. This is often also called as bypass heat transfer, as because the heat is as if bypassing from one plate to the other and bypassing the fluid. So, as if directly this heat is QA is going from the fluid to the other separating plate. So, now if we look into this situation, there may be another situation where this fluid stream is such that this is like this, where this is Ta and this is at Tb, and the fluid temperature the intermediate fluid, which is the flowing the convective fluid flowing over the fin, you will have a temperature T0, which is intermediate to this Ta and Tb. So, in this configuration also we will find that the fin temperature is at the there is no extremum located at this point. So, at some point or in between, say we have said that e to the power 2 mx is equals to that one is equals to e to the power ml minus r by r minus e to the power ml. That is what we have found for that fin equation where we got an extremum. But for this situation where at some point this fin temperature profile will have same temperature as that of T0. So, here in this case that will correspond to a configuration where we will find that this situation is similar to that e to the power 2 mx. So, at some point theta at some point for this situation where we are talking about, say here this is T A and this is say T B and this is where we have T 0. So, at some point x we will find that the x this will correspond to a situation where the theta x itself will vanish. Because it will be similar to the T 0. And now, in this case this will be e to the power 2 mx and this will lead to the situation e to the power ml minus r divided by e to the power minus ml minus r. So, this is different from the previous situation and this will also corresponding to a different situation which giving rise to a different kind of heat transfer, and particularly that will lead to all the earlier cases also where we have talked about that when the physical it lies the maxima or the minima lies beyond the physical boundary of the condition, or when the situation is such that the fluid temperature is in between T A and T B. That kind of situation, how do we taken into account in a real situation which we do not know. When there are multiple fluid streams arranged in different layers and there may be different situations arising, and during that time the analysis or the fin analysis should be such that they will be automatically taken into account of those situations. So, although we have estimated Q A and Q B, now we will look for whether it is sufficient to take account of the heat transfer from this wall to the fluid or from this side to this is adequate, or we have to look for something else which is taking account of the axial the transverse heat conduction or the bypass heat transfer, and then we will be able to we should not be worried about whether it is already taken care or not in the analysis. So, that we will look in the next class, and thank you for your attention.